And then you said BBA. It doesn't really mean anything.
It doesn't. Okay, but what is it? What do you mean donate what? Proton or an H plus to what? To a base, right? So they have to donate to something. They donate to the base. So the Bronsted acid is more inclusive. Sorry, Bronsted acid in bases is more inclusive because it has kind of a more applicable definition. It's broader because it's not just in water. Arrhenius' definition is just in water, so that's why Bronsted Lowry expanded the definition of what an acid and what a base is. Lewis acids and bases deal with what? Right, lone pair of electrons. And how does that make sense though? What else do we associate the word Lewis with? Lewis dot structures, which deal with which deal with lone pairs of electrons. And then which is the acid? Is it the lone pair acceptor or the lone pair donor? Acceptor. So I remember it. Acid is the acceptor in this one, and that's the only one that is different than the rest of them. The rest of them, the acid is the donor of an H+. So it should make sense that the acid is the acceptor of a lone pair because H+ are pretty much opposite of lone pairs, positive charge versus negative charge. So that should kind of make common sense. Give me an example of a conjugate acid-base pair. Ammonium. So ammonium ion and so when I say this is the tricky part. When I say conjugate acid-base pair, I mean the thing, and then the thing after it's either gained or lost a proton. So we had ammonium and ammonia. Which is the acid? Because it's got the extra H+, right? So this is this actually I would call the conjugate acid because it's actually a conjugate, but I'll put acid here and this would be its conjugate base, or if I put conjugate acid, I would call this the base, vice versa. So it's a pair. So what's really the difference between a conjugate acid-base pair? What's the difference between them? One proton, that's it. So don't get that wrong on multiple choice. Make sure you're like, oh, let me tell you about this and then this other thing. Like, no, it's got to be the same thing. It's just one difference. Amphoteric means what? Right, so the best example, water. That's why it forms equal amounts of hydronium and hydroxide because it can do autoionization through amphoterism. We know our 6 strong acids and 6 strong bases. Yes?
Yeah.
Okay, I've reviewed this with honors a lot, and sometimes I think I've reviewed it with you, and I can't remember. So I'm just going down the road. I need 6 strong acids. 6 of you.
HCl.
Okay.
HF.
No. HCl. No, HCl is correct. HBr. Say again. H2SO4. H2SO4 is sulfuric, right? Guys, keep going. Nitric acid. Sulfuric, and what else? Perchloric. Okay, sometimes you'll see chloric acid as well. My people talking now. You'll see you'll see perchloric and you'll see chlorous as well, which is which is AClO3, but perchloric is the best one to use for your 6. 8 strong bases, do you remember how to decide that?
Big B on the left side.
Right, it's the little b on the left side, so I'm going to point over there. So where does it start? Lithium, there's 8 of them, okay? 1, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, barium hydroxide, strontium hydroxide, calcium hydroxide. Little b.
Wow.
See it? Okay, cool. So this is a quick review. We all should know I skipped this. Ion product constant. What the heck does that mean? Okay, I'll give you a hint. What does product mean in math? Multiplication. Okay, so what do you think I'm multiplying? Ion concentrations, and it's a constant. What constant do we usually refer to? K. So Kw is the ion product constant. It's usually called the ion product constant of water, but we generally just assume it's for water. So what is going to be what are the 2 ions involved here? Hydronium and hydroxide. And what does that equal? Negative 14th, right. So 1 times 10 to the negative 14th. At 25 degrees C, it can be different at other temperatures. 3 equations we commonly use. pH is equal to?
14 must be
What? pH is equal to, okay, okay. This is what I was specifically looking for, and then I also heard pH is equal to 14 minus the pOH, so 14 is equal to pH plus pOH. And then how do I get to hydronium concentration from pH? Okay, how do I do anti-log mathematically, not?
10 to the power whatever.
So hydronium concentration is equal to 10 to the negative pH. So if the pH was 4, what's hydronium concentration? So 1 times 10 to the negative 4. If the pH was 7, 1 times 10 to the negative 7. That's what we can do with pH stuff in our head sometimes if the numbers are base 10. If we had to, I don't know if I want to, if we had to, actually no, right here, can you decide right now, knowing the hydroxide concentration, if this is acidic, basic, or neutral? Why?
It's acidic.
It's basic. It's definitely basic, but why, Clayton?
Because it's bigger than 10 to the 7th.
So the hydroxide concentration is bigger than 1 times 10 to the negative 7th, which means that there's surplus of hydroxides versus hydronium. Hydroxides versus hydronium. So it's definitely basic. How could you easily in one step find the hydronium concentration?
Concentration to the divide by 10.
So I would use the Kw constant divided by hydroxide to get hydronium. Because that's hydronium times hydroxide gives you Kw, which is 1 times 10 to the negative 14. Okay, what is true about hydrochloric acid when it goes into water? Okay, so I'm looking for 100% ionization, so I would draw a double-headed arrow or single arrow? Single arrow for H plus going to, HCl going to H plus and HCl. So, wow, hold on, did I go backwards? There you go, okay. I didn't realize this thing was so long. So down here again, so I draw the single arrow to indicate that this is 100% dissociated. So what does that mean? I can automatically assume about hydronium or H plus concentration.
Same concentration as
Right, so if this 100% goes, then I automatically assume 0.025 molar is the hydronium, hydronium concentration. Give me an approximate pH. Yeah.
I have a question. Does that actually happen?
Yes, there's no such thing as HCl. There's only in solution H plus and Cl minus.
So you can just add as much as possible.
Yeah, that's why we have really super concentrated stuff, because it just keeps on making H plus.
That's cool.
So, what is an approximate pH for this?
2.8.
Okay, tell me how you got that.
Okay, so it's 2.5 times 10 to the negative third. That's
So, okay, so this,
And since it's 10 to the negative third, and it's a little more than 1, I figured it's a little less than 3.
Okay, we double check the calculators, do the negative log. But yeah, what you do is whenever you can write it in scientific notation, it's much easier. So if this is hydronium concentration, pH is equal to the negative log of 2.5 times 10 to the negative third, where negative 3, that exponent represents the maximum pH it can be. So the maximum pH this will be is 3, but since you know this is not 1 times 10 to the negative third would be a pH of 3. Since it's more concentrated than 1, because it's a 2.5, it's going to be inversely related, so pH goes down when concentration goes up.
2.6.
2.6. I'm sorry. So we know that it's maxed out at 3 because of the exponent. And then calcium hydroxide, what happens with it?
hydroxide.
So it ionizes completely, but to what?
Ca2 plus 2 OH minus.
That's what I want to hear, is the fact that there are 2 of these. So then what do I assume about the hydroxide concentration? So I'm going to transpose this here. You need to write this down. So if it dissociates in a 1-to-1 mole ratio with calcium, that's automatically the calcium concentration. But what's the hydroxide concentration? 2 times that, because it makes double the hydroxide. So this will be 0.009 molar. So then what's an approximate? So this is hydroxide concentration, 9.0 times 10 to the negative third. What is the approximate pOH?
13.
Give me pOH. It's approximately 2.1 or something like that. Because the max pOH, because it's calculated the same way, negative log of hydroxide concentration. POH is going to be the maximum POH is going to also be represented by the exponent, so the maximum POH would be 3. But 9 is almost 1 times 10 to the negative second, because it's on the high part of it, or the larger side. So maybe the 2.1 we'll say. So if the POH is 2.1, this of course is approximating, what would the pH be? 11.9, which is basic, which we would assume to be for such a strong base. We double check the math. Negative log of 9.0 times 10 to the negative 3. What is it? 2.04. Okay, so we were close. All right, so do you feel more comfortable with the basics? Quick review. Okay. Sorry, I didn't mean for that to happen. It happened. All right, so we did that. This information here is going to have you use your mixture information. So I want you guys to take maybe 10 minutes max. I have 3 examples. Because I can assume that you understand it, but I want to make sure you're okay with it. So there are 3 different types of examples. So from your last bit of notes from last night, you can read the person next to you. Take this as little time as you can. And I'll come see your outlines while you guys start those. I don't know that I printed these. Let me double check. I'm a good person. Yes. You're the first 3. This is the part that was new to you, so I know for sure you should have written this part down. I'm just going to quickly come around so make sure I can see your outline.
Why did we go into overtime for 5 seconds? Why was it a 5-second overtime?
No, it wasn't. That wasn't
All right, sorry to bother you. Go back and focus because I'm making sure we get through as much today as we can for your own sake.
Okay. I was gonna say, I pulled out honors. It's exactly the same except for the, yeah. I get my whole honors.
in there. But then you just use one of these.
We'll do auto. We'll do percentage. It's not very good. Nothing that's really. Are we on the first booster or in the second one?
Second.
Okay, fine. What did you guys do? How about I'll be third party and I'll be so we can assume he's wrong, right, Clayton?
Oh, both of you are recording.
Oh, you are. I'm the only one that's right.
Oh, you're right. I didn't say. Wait, quick, you on now?
I'm just gonna watch it.
Oh, that's the pH. 1.1. I'm doing POH right here. I'm showing all my steps for just a second for the first one. All right, who got 12.90? Okay, why are we recording 2 decimals after pH? 2 sig figs because of what? 2 sig figs from what? Concentration or the molarity of the strong base. Okay, so quick recap. If you have a strong, first of all, we should recognize that a strong base and weak base immediately so that you understand that this one is not dissociating appreciably, so therefore the hydroxide concentration is minimal. Only the strong base is making enough moles of hydroxide to make a difference. So I went ahead and went to millimoles. Actually, I didn't show any of my final calculations except for it's really much at the very end. But if you use your milliliters, please don't interrupt right now. If you use your milliliters or the volume of the strong base multiplied by the molarity, that's going to give you millimoles. And then I chose to divide by the total volume in milliliters, so millimoles over milliliters. Millis cancel to be moles over liters, so that's why it's molarity. So I don't actually convert to liters at all, and that's on you if you want to. I'm a millimole person. Once you get hydroxide from the strong base, then you're going to plug it in the POH, and then 14 minus the POH. If you'd like to just do one step, you can do 14 minus the negative log of hydroxide, and that gives you the pH immediately. So that's how you can combine these 2 steps into one. Who got that though again? Some of us who didn't. What did we do wrong? You went to mole. You did what?
Were you supposed to put volume like with moles, and that gave me a cancer crystal.
So are you talking about volume up here, or down here? You have to put, yeah, because it has to give you a molarity, it has to give you a concentration. So if you have moles on top, you have to divide by volume to get to molarity. Does that make sense? Oh, okay. All right, next one, tell me your process. I think I want to make sure everybody's on the right track on this one. What's your process? Or what do you identify first? So they both attribute to the hydronium concentration? So then, what did you guys do?
10.2.
So 10 milliliters for the nitric acid times it's 0.2 molar. So there's you millimoles of H plus from nitric acid. And then what'd you do?
15 times 0.5.
So you added, so you're adding, so this is from nitric acid, and you're adding the 15 milliliters times 0.50 molar, and this is for hydrochloric acid. What are the units that I'm in right now? Millimoles, right? So milliliters times milliliter. That just basically means millimoles over milliliters. So the milliliters cancel out to give you millimoles of this, and this is actually H plus, and this is millimoles of also again H plus. These millimoles will be added and then divided by what? 25 milliliters total volume. So I like to just put volume total down there to remind you we did add 10 milliliters plus 15. This gives us our hydronium concentration, our H plus concentration to be. Actually, yeah, I got it. I sometimes just go straight to the actual calculation. Yeah, so 0.38 molar. So 3.8 times 10 to the negative 1 is about of 1. No, sorry, pH is like 0.42. So negative log of the hydronium is 0.42 molar. I mean 0.42 for the pH. So that was strong. Last one. Right, you gotta do VDA. And so I'm choosing this 1-to-1 ratio one over the one that's a little bit more complex. I'll do that one if I need to later, but let's start with this one. If you have an acid and base together, they have to react. So you have to write it as a reaction. Oh, and while I'm thinking about that, if it ever says on a question, dissociates with water, or ionizes in water, or show its solubility in water or something like that, it's not talking about reacting with water. So do not even put water as a reactant. Just understand, like, what does it do in water? It splits up, it makes ions, whatever it is. So reacting is different than putting in water. Does that make sense? Some things just dissociate in water, some things actually react with water. If it doesn't say to react with water, then don't. All right, so sodium hydroxide plus HCl yields NaCl plus water. What's your millimoles here for sodium hydroxide?
0.002.
I'm just going to go milli just to kind of show you another perspective. So if you do 10 times 0.2, this is M times V to give you millimoles. So what's 10 times 0.2? 2 millimoles. You can do this in your head, right? HCl, what's 15 times 0.5? 7.5, so half of 15. 7.5 millimoles. Who's your LR? Sodium hydroxide. So then what do? So subtract 2. Add 2, only because the ratio is a 1-to-1. So this is going to be 5.5 millimoles of HCl left over. And then what I'd like for you to show me is how does that impact pH? This is equal to 5.5 millimoles of H plus. And that's because that's the part that's actually important. So it's just because there's one H plus here. And then do what? Yeah, divided by total volume of 25 milliliters, and that gives us our hydronium or H plus concentration to be, thank you, 0.22 molar. So then pH, negative log of 0.22 is 0.658. Don't know why it's 2, give me 6, 0.69. 6. Thank you. This looks good here. So mixtures, we're okay with. There's basically 3 types of mixtures. So the only one that's different is if you have a ratio that's not a 1-to-1. You just have to watch your stoichiometry as you do your VDA table. All right, so let's jump into Ka. Can you imagine what Ka stands for? I hope you know a little bit.
Something about acids.
Something about acids. Well, what does K stand for? It's the equilibrium constant, okay? So with acids, it's the acid equilibrium constant, but it's actually phrased a little different. It's called the, I'm not going to make you guys, do I need to make anybody else do any more?
Oh, no.
If you want more, there's plenty on your sheet, okay? I skipped over some stuff. I'm going to hold, yeah. Do I want to hold off on this? No, I have to do this. I'll go back up to the pictures in just a second. We're going to talk about K in just a second. We already talked about the 100% ionization, how when these things dissociate, this is how we write dissociation of an acid. This one you have to write water in the reaction because the fact that an acid dissociates, the formation of hydronium is really the most important part. Hydronium does not form outside of water because it has to have water to donate the proton to. And really, this is indicating not only the fact that it's an acid, but it's indicating it's a Bronsted acid because what is it doing to water? It's a Bronsted acid because it's doing what to water? Right, it has to donate the proton to the base, and in this case, the water is acting as the base. So in this one, whenever you have a dissociation reaction, you must write it like this. And I'm showing a single arrow because this is representing a strong dissociation. Therefore, the hydronium equals whatever the acid concentration was. I do believe that we're good with this because we just practiced this like 3 times. If you have a strong acid and a strong acid, you find their millimoles of both and divide it by the total volume to get the hydronium. Good there. Thumbs up, smile, something. Okay. This is just review. All right, this is the part that's new. And we actually talked a baby bit about this in honors, my class, so you might remember a little bit. But this is representing a weak acid undergoing dissociation, but it's weak, and you can see that because of the reversible reaction here. It still makes hydronium, but it makes like 1% hydronium. It's very, very, very small. So what can you imagine the K value would be if it's making very few products?
Very small.
Very small, so give me a number.
10 to the negative 10.
So 1 times 10 to the negative 10. It might even be smaller than that. Sometimes they are incredibly small because it makes such a minor amount of product. So if that K value is that small, it's going to indicate which side is definitely favored. Reactants are highly favored. So if I had a bottle of this magical HA solution, this weak acid, what would I find in that bottle? HA and water. And if I looked really, really hard, I might find 1 hydronium and 1 of its anion after dissociation. Okay, so it's going to be very minor. So we have to be able to talk about how does this relate to to the ionization constant as well as percent ionization. So if you need to write down any of this, we're going to start a problem here in a second. So most of you guys don't write notes, and I think that's okay. I don't mind, but I just want to make sure you're having things look back in the reference. Okay, so in this example, we're talking about a weak acid undergoing dissociation. It's going to partially ionize by some amount, I don't know, and I like to call that amount X. Okay, and then at the end, I'm going to actually set up the K expression and determine the pH. We are doing an icebox. Now we're doing ice, we're doing equilibrium in the theme of acids and bases now. So let's write the ionization of hypochlorous acid. What is hypochlorous acid?
HCl.
HClO. And when it reacts with water, what does it make? And okay, so this is a weak acid. Why? It's not one of our 6, right? Everyone's like, oh no, it's not one of our 6. What do we know initially? Let's go ahead and set up our Ka expression. What is our Ka expression? What's our K? How do we always write our K expressions?
Oh, concentration of H.
Okay, so the concentration of products, which is hydronium times hypochlorite divided by
HClO.
the reactants, right? I got you. Okay, and no water because water is liquid. All right, this is not new. We got this. All right, sorry, you scared me. What do I know for ice though? What do I know right now for my problem? Where does it go? Under hypochlorous. Okay, so I know 0.1 molar is hypochlorous's initial concentration. I don't have anything to do with water because it's a liquid. I don't have 0 and 0 both products because it doesn't tell me, and it's before the reaction actually begins. How much changes? I don't know. What do I call it? X. So I'm minusing 1x here, adding 1x here, adding 1x here. This is not new either. 0.10 minus x, x, and x. Well, the Ka value, I have to tell you, where did I put it? 3.5 times 10 to the negative 8. And these values are all online in the back of your book, big charts of them everywhere. I usually tell you what it is though. 3.5 times the negative 8. So that value indicates one, the products are not favored, the reactants are highly favored. So what can you imagine X is? Maybe small enough to neglect?
Yes.
Let's try. All right, so in this equilibrium, you're going to plug it into Ka, solve. Now I'm setting up the ice box all the way. If you want to minimize it and just put, you know what's going to happen, 0.1 minus X, X, instead of setting up the entire box, that's totally fine. So I'm going to plug in K X squared over 0.1 minus X is equal to Ka. But then, like I said, we're going to try to neglect. So solve this with me. Neglect, so you assume that's 0. So then X squared over 0.1 equals 3.5 times 10 to the negative 8. If you can set that up for me and then solve from X from there, you don't have to show me the baby steps of, okay, multiply by 0.1 and then square root. So what's X? 5.9 times 10 to the negative 5. Okay, so in this case, what is X representing? That's so important for us to find the pH. Right, this is representing hydronium. It's also representing, hypochlorite, but nobody cares about that because it doesn't have anything to do with pH. So this is representing hydronium's concentration. Before we take that and find the pH, let's make sure we can neglect that. How do you do that?
5.7.
How do you do that?
Put that value over the lowest value that you were subtracting.
Okay,
Right.
so you're doing, basically you're trying to figure out if that's less than 5%. So 5.9 times 10 to the negative 5th divided by 0.1 times 100. That is, I don't have it written down. I can tell it's less than 5%, but it's like 0.1%. 0.06%. Okay, so it's definitely negligible, right? Okay, so then what is the pH? Can you give me an approximate pH before you actually plug it in? 4 point, maybe 4.2 or 3. Let's see. So the max is 5 because the exponent's 5, so we know it's less than 5. So then 4 something. Tell me what pH is. 4.2. You're going to be like magicians in the math class. You're like, yeah, that log is like 4. You're like, what? Actually, you guys are way out of logs in class. Okay, so does this make sense for an acid? Yes, because it's acidic. Does it make sense for a weak acid? Yeah, it's between 1 and 7. It's not close to 1. It's not too close to 7. It's in the middle range. It makes sense for a weak acid. It does. Okay. I messed up my slide down here. So this is the last part on like new stuff. We'll practice some more. The strength of an acid is sometimes you sometimes refer to the strength of an acid based off its percent ionization, and its percent ionization is X, but it just now has a name to it. So percent ionization is going to be something that comes up on multiple choice, and I don't want you to be like, I don't know what this term means. It literally means the amount of hydronium or H+ that come out of a weak acid in water. What's up? So in this case, that first example, the percent ionization is actually what our 5% rule indicated. Do you realize that? So what in that first example up there, what would you say the molarity of the ionized acid is? Say again? No, just the molarity of the ionized acid. 5.9 times 10 to the negative 5th molar. Because that's the amount of hydronium or H+ that was created from the acid in solution. What would you say the initial molarity of the acid was? 1.1, right? Doesn't that look like the 5% rule we just did? Right. And so the 5% rule is based off statistical differences, p-values, but it also indicates exactly what we're looking for. How much stuff ionized over how much stuff I had originally. So this is 0.06, which thank you, Alex calculated. So tell me, does that scream it's a weak acid?
Yes.
Does it ionize very much?
No.
No. So some of us are like, well, how do you know the percent ionization of an acid? How do you just assume? I'm always say it's like less than 1 or 2% because it's usually very tiny. Strong acids have 100% ionization. There's really nothing in the middle. Okay. what do I want to tell you here? Oh, if you're trying to figure out, so we know that acids have a tendency to dissociate, but they actually dissociate in the presence of stronger bases better. And so water is not a very strong base because it's amphoteric and acts as an acid or as a base. In this case, we're going to talk about, and this is just a basic anion, basic anion. And if that anion is a really strong basic anion, just meaning it can attract the hydronium or H plus better, it's going to actually keep this together and will not allow it to ionize, so it's going to not allow it to make H pluses, which means it's not going to be a strong acid. If you have a stronger attraction, it's going to be a weaker acid. And then separately, there was something else, oh no, I have it next. In one of the videos, whenever it talked about making conjugate acids and conjugate bases, it talked about the strength of the conjugate acid and the strength of the conjugate bases. You'll do some reading on that too, but we're getting ready to get to that. Okay. Oh yeah, so I will actually tell you, no, I want you guys to do this. I want you to go ahead, let's do U6, do the ionization of acetic acid of 0.1 molar, and then this group do 0.1 molar, and then this group pick one. Okay, do an icebox. Let me tell you the Ka for acetic acid. 1.8 times 10 to the negative. Let me verify that. That's from memory. Yeah. Same process, it's just I assigned different concentrations for you guys. Group 1, what did you guys get for your X value? The first question. Anybody? 0.00134.
Oh yeah.
I'm the scientific notation, so I'm sorry, I'm ready. 1.34 times 10 to the negative third molar, which is our hydronium concentration. Group 2, what did you guys get for hydronium? Or for X?
4.24 times 10 to the negative 4.
X is equal to what again?
4.24 times 10 to the negative 4.
Oh yeah, that's what I got too. Sorry. Wait, what in the world? 4.24 times 10 to the negative 4th molar. Okay, I want everybody to also calculate their percent ionization. So your own percent ionization. which is setting it up just like we did for evaluating the percent or the 5% rule. Group 1, what's your percent ionization?
1.34.
So you just did X over 0.1 times 100, you got 1.34% ionization. Is that indicative of a weak acid? Totally, right? That's 1% ionization versus 100% ionization. Group 2, what'd you guys get?
4.24.
Okay, so this is the funny part. You're dividing by 0.001, or 0.01, sorry, molar, times 100. You got 4.24. Alright, everybody consider the information given and tell me if you can come up with an explanation why we have a 0.1 molar solution dissociating about 1%, but we have a 0.001 molar solution dissociating at 4%. Why is this one more? Why is this one dissociating more, though it's more dilute? Okay, what does the water do in terms of the shaft? Why is it shifting right?
Because you're decreasing the
You're decreasing the what?
You're decreasing the amount of.
Look at here's the reaction right here, right? So if you're looking here and you're explaining what the water, so dilute means there's more water than stuff, right? Why would the water, the overpresence of water, cause this to shift right? Which is essentially what's happening here, because that's why the dissociation is higher. I explained this for you for the acetone part of the Lechat's law. I'm hoping you can kind of help me out here. Okay, so a diluted sample causes these ion concentrations to be in more water. So more water means that these concentrations are technically lowered, right? So as this is lowered in the equilibrium, it's going to continue to further shift it right to dissociate more. So it's because of the diluted samples of the ion concentrations. This one has a lesser chance of dissociating more because it's already kind of at equilibrium. There's no extra stress on it. So that's why this dissociates more. So for a given weak acid, the percent ionization blinks as the acid becomes more dilute. What happens to it? Increases. For a given acid, the percent ionization increases as it becomes more dilute. And that's a fact. That's just a fact to know. And I give you more explanation, like in comparison of Q versus K. You can explain it in many ways, but I just like the Lechat one because it's more qualitative. If you did want to talk about like plugging in those diluted concentrations as products, that means the Q value would decrease. Q value decreasing means it's less than K. Less than K means you have to shift right. So this is kind of review, but I give you some more information, background information. More concentrated stuff means technically they would shift left and it would decrease the ionization. But you'll notice it's still a fairly low value, indicative of a weak acid. So you guys can go back and see some of this because I want to make sure you have the qualitative response, but you also have a quantitative one too. So I'm trying to think if there's anything else we really need to say. Not really. You can always compare Q to K. It's a really easy way to do it. You can also always use Lechat's, but those go hand in hand. Lechat's more qualitative. Q versus K is more quantitative. Okay, I think we got like 2 more examples I want to run through, and I'll go back to the pictures I skipped earlier. I'll go back to this if I need to. So, in this example, I want to work backwards, basically. So what am I giving you in this example? Do I have this on your paper? Do I have this one? Towards the bottom, I believe. Number 3. So fluoroacetic acid, blah, 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 is a stronger acid than acetic acid. Can you tell me right now what you know about fluoroacetic acid versus acetic acid then? This is number 3 on the upper, sorry, on page 2. Number 3 on page 2. Sorry, they're small. This is a huge packet, and I'm going to go over my copy count, but whatever, it's fine. I'll just get yelled at again. So what do you know from the first statement about fluoroacetic acid versus acetic acid? So this one has a what? So Ka of this one is bigger than Ka of this one, because a stronger acid has a bigger Ka, a weaker acid has a lower Ka, because it's going to dissociate more so. So what can you assume maybe about its pH if they have the same initial concentration? If you have to, I'm just pulling some conceptual stuff out of you first.
It'd be lower.
Because it's more acidic, right? Lower pH. Remember, they're indirectly related. Okay, so we know that information. In a 0.1 molar solution of this acid, the pH was measured at 1.96. Calculate the Ka for the chloroacetic acid. So, what do you want to do first? What have I been doing first? Setting up the ice, so setting up the BCE first and the ice. So, chloroacetic acid, you have to write it out reacting with water to show the acid-base characteristics here. So, this is the acid. It's donating to make hydronium and chloroacetate. Did I write that? Right, okay, I did. And then, what else do I know here? So, 0.1 goes where? So it goes in I for this guy. What else do I know? But what does that tell me really?
The concentration.
Concentration of what? Hydronium. Okay, so this, how do I get to concentration of hydronium? So 10 to the negative 1.96, which is, I don't know. I have to look at my paper for that one. 0.01. So hydronium, and this is, and I'll tell you, I'm putting it at equilibrium because I can't have this by itself, just that by itself is not acidic. Even though it's an acid, it is not acidic. Just that. It's only when it reacts with water and it makes a little hydronium when it gets acidic, because the presence of hydronium is the only thing that makes the pH drop down to basic or acidic region. So this has to be at equilibrium whenever you write it in here. Okay, so that's all I know. Fill in the rest, and we'll talk about the Ka. So what else can I fill in immediately?
The initials.
Right, so I know the initials for both of these are 0. I know water is irrelevant. What else do I know?
The change.
The change for everything, right? So I actually know X. I'm not going to put X's in. I know X. I know this is plus 0.01096 plus 0.01096. This is subtracting 0.01096. So then this value is
0.08904.
thank you, 0.08094. Is that what you said?
0.08904.
904. I sometimes just plug that in my calculator versus actually finding it. But since we get this the same on both sides, we now have the values at equilibrium. We can plug into our Ka expression and solve for Ka. So you guys tell me what your Ka is when you get there. I like to make you at least participate, practice, actually calculate in round 1 and 2 of doing these problems so that you have mental memory of, or muscle memory of what's going on. And you usually get points for your expressions, so put your expressions as often as you can, even though this one is a little long. So you got 0.01096 squared over 0.08904. What'd you guys get? 1.35 times 10 to the negative third is our Ka value. Okay, so if that's a Ka of chloroacetic acid, what would be a Ka for acetic acid, based on the first statement?
Less than.
So
1.35 times 10 to the negative 4.
okay, so something with a lower exponent, 10 to the negative 4, 10 to the negative 8. Acetic acid is actually 1.8 times 10 to the negative 8. Okay, I have a couple more like conceptual things to tell you, and I'll let you guys practice your Ka problem set. So this is the information I was talking about earlier about the relative strength of conjugations versus bases. Write this down. Write down something about it, about each bullet point. I'll scroll down in a second, and I'll explain as we go. I'll give you a second to read and write down what you need to. Langdon said if anybody needs help learning how to use the registration online, to let you know. So let me know within class. I think most of you guys did it last year. Online. Yeah.
Okay, so you're gonna be about that. I just wanna know who in here is taking AP bio last year. Some of you might have taken it. Just don't know how I do this to myself again.
Wow. Not even knowing it's not working.
I was just asking because I heard AP bio was in his bed. Just
I'm in the room.
no, I mean like this is one that
I heard it was much less.
Things
class
was-
is not.
I hear a lot of people say
it's not as bad
It's like AP Chem.
as in hard. It's just it's a lot of
Can
work.
either
but
confirm
it's
or
not
deny.
like-
It just depends on like
easier this
bio is more
I've heard.
conceptual and it's a lot of memorization. This is more problem solving. I didn't take AP bio in high school.
One of the exams really easy on your GPs.
And you're cool biology major.
By accident.
I asked.
Should have been a chem major. Should have been a biochem major.
Yeah, I didn't know this. Like she really taught herself chemistry.
Yeah. I don't want to even admit like what I didn't know before I started doing chemistry.
You said, wait, you told us that you
I couldn't even
know
tell you.
what
NaCl.
sodium chloride, like the compound looked like.
I couldn't even tell you like how to crisscross. I didn't know it. I forgot what charges were. I forgot what crisscrossing charges. I forgot how to like you chose the name.
And this was like the first year you taught it, right?
This was the week before I taught it. So anyway.
Long story.
Okay, so whenever we're talking about the strength of an acid, the strength refers to what again?
The ionization.
Right, the ability to ionize. All right, work with me here. This is conceptual. So if I have HCl going to form its two compounds, work with me. Thank you. So when I have an acid dissociating, it technically could go back. We've seen that. That's what a reversible reaction is. So if it can go back, it's going to be considered, one of these will be considered the acid, one of these will be considered the base, or the conjugate acid, conjugate base. But in this case here, this product is such a weak conjugate base. Why is it a weak conjugate base?
Because it's H plus.
Okay, so it's an H plus. It's the product of a very strong acid. So a strong acid they always make conjugate bases. Okay, so acids always make conjugate bases, but this is such a weak conjugate base because what is the job of a base in solution? What does it do? In like a Bronsted base,
It accepts.
H pluses, right? So would that ever accept an H plus? No, I've never seen that 2H 2 plus, never in my life. Okay, that's such a weak conjugate base because it won't do the job of a base. But something like acetic acid going to this, and I'm excluding water for the moment, but you know, water is there. Actually, yeah, which here, between this and these two, we know this is the acid for sure. Which of these is the conjugate base of it? This actually is the conjugate base. I don't know why I labeled this one. This is the conjugate base. This chlorine here, I'm going to backtrack. This chlorine here will not react back with H plus because if it did react back with H plus here, it would reform hydrochloric acid, which immediately would then again ionize. So therefore, it's a weak conjugate base as well because neither of them will have the ability to accept H plus back. So anyway, this is our weak acid. Which of these is its conjugate base? Right, so this is its conjugate base. Is this able to accept an H plus back?
Yes.
Yes, and so this is a stronger conjugate base because it can accept it back, and it does very readily, which is why you see predominantly acetic acid in solution versus these ions individually. So what can you probably look at and determine the weakness or the strength of the conjugate base? Probably the Ka value. So a very, very high Ka value would mean that the conjugate base is very, very weak, so it's not going to go back. But a very low Ka value would mean like, yeah, it's a weak acid. It's going to make a strong conjugate base. And if it makes a strong conjugate base, the conjugate base will react again to reform the original acid because they have a stronger attraction for the hydronium. And then there's a ranking system for oxyacids. I'm not sure if you can tell here, but the ranking system is based off the number pretty much the number of oxygens. And I'll go back to the pictures in just a second for you because it makes more sense from a particulate diagram. These right here, 4, 3, 2, or 3 and 2, and then we actually can go down to like hypochlorous acid. The oxy acid itself, which is just an acid with oxygen in it, the more oxygens, the weaker. Alright, so the more oxygens, the weaker the bond between H and, I'm going to say polyatomic ion. Usually it's a polyatomic ion that's attached to. So if there's a weak bond between the H and then the whole other part of the molecule, what's going to happen to that bond more likely? I think a picture might help. I'll scroll back for you. If I have, hold on. So for example, this bond right here, you'll see this is sulfuric acid, right? Was this the stronger side or the weaker side on that scale you just wrote down?
Stronger.
Okay, this is definitely a strong acid. You know sulfuric acid is a strong acid. It's strong because that bond right there is very, very weak. And so if it's weak, what's going to happen to it? It's going to break off and do what? Make tons and tons of H pluses, okay? When that bond right there breaks, oh, this little mouse is here. When that bond right there breaks, it makes lots and lots of the H plus, which is indicative of a strong acid. And it differs based on the amount of oxygens around it. So this polyatomic ion there, having so many oxygens means there's a large electron density here. And the electron density increasing here means that they're very negative, and they actually pull the electrons towards them. So the electrons are all being pulled towards the oxygens and sulfur, weakening the covalent bond here. Whereas over here, well, that's also a strong acid. So there's 3 oxygens here. The electron density is high. That bond is weak. It breaks very easily. But as I keep going, let's go with this one. What acid is this, by the way? Am I getting ready to make? Okay, so this is the functional group. Remember from the organic chem independent study? This is the carboxylic acid group, which is represented as COOH. That's the carboxylic acid group. But what if I did this? What acid is that?
Years ago.
2 C's.
2 C's.
Hang on.
4 sounds like
Acetic acid, thank you. This is acetic acid. And I want you to look at it as the H's, as 2 different types of H's. This H over here, this is the acidic hydrogen. Why is that the acidic one? It what? It breaks off super easy. There's an oxygen, an O to H bond here, and this whole thing over here, oops, sorry, I forgot the H there. This here is acetate, and this is a part of acetate. These 3 H's here, so that's C2H3O2, 1 minus, C2H3O2. These are never going to pop off. This one will pop off, and this is one on our exam last year on multiple choice. So you need to understand this is acetic acid, and this is the one bond that breaks. Is that bond stronger or weaker than that bond there? Stronger. Why? Yes, but so it's a weak acid because it's stronger. It's not stronger because it's a weak acid. So this is stronger. How was I explaining it earlier?
That would be electron density.
Okay, so the electron density in this case
It's weak.
is not as concentrated because the electrons are distributed here, and somewhat over here. So there's not a very dense location of electrons to weaken that bond. So they are sharing it not equally, but more equally. So therefore, it's a stronger bond, meaning it's not going to dissociate as much. So those are how the particulate models relate to what we've been doing. This is a super strong acid because it doesn't really have any. It's very polar, so it's going to break off very, very well. So very polar bonds relate to breaking and making hydrogen ions in solution. That's really the most basic point I can give to you. More polar the bond, meaning the electron density is in one location, the other side's on the other, or the hydrogen's on the other. It's going to cause the bond to break and make H plus in solution. Okay, yeah.
More polar more likely to break off.
And that's why it's more likely to be a strong acid. I don't know if you recognize, but I know the HS one is different, but H to Cl, H to Br, and H to I, those are all very polar bonds because they're the huge difference in their electronegativity values. Because one's on the left, one's on the right over here. Fluorine is the most electronegative value, but fluorine is so small, it sticks to hydrogen like glue. It's just so small. Their nuclei, their attractions are very high, so it does not dissociate very well. All right, I think that's all I want to tell you guys today, except for the pKa. Okay. Sorry, there's one more thing. We have like 20 minutes left. This you'll do in your homework tonight. I'll skip that for now. This is the last thing that I need you guys to write down. And tell me if it makes sense in terms of your mathematical knowledge. What does P mean? P in terms of like pH.
The power.
Okay, so like power of the potential of hydrogen.
Yeah.
pH means potential of hydrogen. And anytime I put P in front of something, what function does that mean? Negative log. So I can put P in front of anything, and that means you're taking the negative log of that, whatever the thing is I have there. So I can have pH, and you do the negative log of hydronium. POH, that's the negative log of hydroxide. I can do pKa, and that's the negative log of the Ka value. And there's a reason we do this. It's because it's really, really important when we get to buffers. But there's a relationship between the number for pKa and the Ka value. So just like pH is inversely related because of the whole log function and the fact that it's got a negative in front, increased pKa means what for its strength, its acidity. So a high pKa value would mean that it's taking, so just like, okay, so tell me this, a high pH value, what does that tell me about the acid? It makes low numbers of hydrogens, so it's also a weak acid. So that's the same way. If I have a high pKa value, it's a weak acid because it's got a low Ka value. So if it has a low Ka value, it means it just doesn't dissociate very much. So it's got the same directional relationship, it just means something slightly different. And I can easily do that for KBs. What do you think B stands for? KB means for base. And I would be doing, you guys will be doing values with that tomorrow. Okay, it is 8:20. You can either look at your acid-base pH practice. You see 1 through 7 right below where we were working? Yeah? 1 through 7 on page 2. Answers are below. That's one thing you guys are working on. You got it? And then on the website, there's a reading from NSMI acid-base equilibria, and I have the questions denoted on the homework website. I haven't written them up there yet, but you're going to kind of quickly outline that one because you'll see there's a lot of repeated information for acids. But I really want you to expose yourself to bases and salt hydrolysis before tomorrow, so that our notes make sense, because I won't be here. I have to go write the curriculum for the county, which they will do on my own time. I'd rather not be. I'd rather be here. What's up?
What's the homework?
That's what I'm going over right now.
Yeah.
So 1 through 7 on this problem set right in front of you, and then the outline. You guys are going to do problems within the outline. So I just need to pull it up for you to see what it looks like. Okay. But we have 12 minutes left in class. Either work on that or finish your test from yesterday. I would like for you to finish. If you are done and you're like, I'm done, then sit where you are. If you would like to try to finish, scatter. Just because I don't still know if it's too long or if it's you guys, and I'm going to have you do a survey. Go, scatter. I know your brain is full. Actually, your brain's not full. Your brain holds a lot more. Okay, if you are using,
I don't think it can do any better.
or I can take these. Be quiet for me. If I call your name and you want it, come grab it. Maggie, Han, Lewis, Donkey, Justin, Shannon, Nick, Alex.
Do it in a different color, huh?
Yes, I'm sorry. Please do it in a different color so I know where you stopped and started. Jack. I circled some of it, but you guys were close. Chitra, Clayton. Shannon, yours is here. Scooch the other way, girly. Scooch this way, thanks. What did I just say? Clayton, Nathaniel, Simon, Josh, Chelsea. That's all I got. If you want to, it's up here on my desk. Or Kevin, you go. What's your name? There it is. You need yours? If I color attention, you have a spreadsheet right here.